Okay, let's talk about gravity some more. And we're going to talk a little bit more about free fall and weightlessness and stuff like that. Pardon me? There's supposed to be a little, yeah, and it does the Doppler effect, but it got broken. Okay, do you need to write any of that down, do you think? No, just some history. During the Great Plague, you guys probably heard about the bubonic plague or the Black Death. You know, if you've watched the Monty Python movies, you've seen it in there. It was 1665, and a young Isaac Newton was home from college and began thinking about gravity because he didn't have anything better to do. A century before him, a fellow by the name of Johann Kepler developed laws to explain the motion of the planets. He observed, actually it was another fellow by the name of Tycho Brahe, who had a gold nose, by the way, because he got cut off in a duel, but that's another story. Yeah, I was in, I think it was, yeah, I don't know. I saw, where was I? I was in a wax museum and there was a bust, a head of Tycho Brahe. Of course, I was the only one interested in it because the guy had a big gold nose. Got into a duel with a guy and got his nose cut off. So he was I don't know, it was just kind of slipped in there. I don't know. Anyway, so Brahe did all the observations, and another guy by the name of Kepler, he developed these mathematical rules or laws that explained where the planets would be. And you remember way back at the start of the year, I talked about the planets were called wanderers because they wandered through the sky. Turned out Kepler had put the Earth at the center, and these laws, they made sense, but they were extremely complicated. But anyways, Newton wondered if the same force that caused an apple to fall to the ground from a tree was the force that pushed the planets around. Now you've all probably heard or seen in cartoons or what have you the idea of Newton getting hit on the head with an apple sitting under a tree. Probably didn't actually happen like that. They think he was probably sitting in an orchard or wandering through an orchard and saw apples fall and realized that as the moon sort of went down in the sky, he wondered if the same force was causing that. So he did some thinking. And after some thinking, he came up with the law of universal gravitation, which says between every two objects there exists a force of attraction. This force is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. And no, you don't need to know that. Okay? Wait, what year was this? It was 1665-ish. Say that again? Oh. He would have written that likely in Latin at the time, and it's been translated, right? So in sort of a equation form, it looks like this. F, between every two objects, remember the old line of attraction to the pencil sharpener needles? Right? Between every two objects, there exists a force of attraction, and this is proportional to the product of their mass. In other words, the bigger I am, the more the pencil sharpener is attracted to me. Right? And the bigger the pencil sharpener is, like say it's the desk instead, well then I'm more attracted to the desk than the pencil sharpener because it's more massive. Okay? And it's inversely proportional to the square of the distance between the centers. So if I'm close to the desk, I'm really attracted to it. And if I'm a little bit farther away, I'm not so much attracted to it. And in equation form, it looks like this. F, the force of attraction, big G is a constant, M1 and M2 stand for the masses, M1 and M2, and R is the distance or the radius squared. Well, because it's like, I mean, if this one is here, if M1 is moved to here, if this distance is the same, this R, then it's the same. So it's like a radius all the way around, right? That's why they use that, right? And again, you guys don't need to worry about that equation. I'm just giving you some background here. Okay? Big G is the universal gravitational constant. If I'm not mistaken, it's 6.67 times 10 to the minus 31. It's a really, 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 really small number. And that would be, I don't even know the units for that. I guess I could work it out, but it doesn't matter. Okay? You're not expected to solve any problems with that. In the good old days of grade 12, we did that, but we don't get near as far as we used to. So, okay. Now, a region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. That's something you need to know. The region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. You all have gravitational fields. Those of you that are more massive than others, you have a bigger gravitational field. My little foam ball here has a gravitational field. It's very unmassive, so its gravitational field is very small. I'm not that attracted to it. I'll go back to that. Can you see these gravitational fields? Can you put on special gravity goggles and see them? No, it's just it's a model, I guess you could say, of what we observe, what we experience, and we use this idea of a field to explain a few things that are kind of tough, and I'm going to get into that in a few days. But you should just, this is your first introduction to what a gravitational field is. And the strength of the field at any place is defined as the gravitational force that a unit mass, 1 kilogram, would experience if placed there. So if I were to go to the back here and get a 1 kilogram mass, incredible. Check. Is that on, Grayson? Yeah? Back there. Hello? Is it on? Can you hear it? Or not? And it's dead. It was charged up too. Check, check. Okay. Anyways, so if I were to get a 1 kilogram mass, hey, right?
Have you ever heard about the Cheerio effect?
The Cheerio effect.
Yeah.
Yeah, about how Cheerios are attracted to each other?
Yeah.
Yeah, I've seen that actually.
Is that like?
I think it is, yeah.
We should go get some Cheerios. Some Cheerios.
I'd actually seen a TED Talk about that too. In fact, if I'm not mistaken, it might even be coming up today. I could be wrong. I was wrong once. Right, I said it. Hey? Yeah, they do. It's got to do with service tension too with the milk. So if I take my 1 kilogram mass, how much force is gravity applying to it right now? About 9.8 newtons, right? Just under 10. If I were to take this to the top of the high rise, would it still show 9.8? Yeah, of course it would, right? But I'd have to go like really high for it to change. For it to be noticeable, I guess. Shouldn't say to change, for it to be noticeable. So the strength of the field is defined as the gravitational force at a unit mass, 1 kilogram is our unit, would experience if placed there. And this strength is represented by the letter G. When a gravitational field line is drawn, and you'll be required to do this, the field lines are closer together where it is strong, and where it is weaker, they're further apart. And it looks like that. Okay, so there's the Earth, and these sort of yellow, greeny kind of lines that I'm going to do in dark because you can hardly see them where you guys are.
You can break newtons and pounds.
You sure can. Pounds is a unit of force as well. I believe it's I know it's 32 feet per second squared, so it's going to be 32 pounds per, how does that work? I'd have to figure that out. Can't do it in my head. So this is what a gravitational field looks like, and where a gravitational field is drawn, the field lines are closer together. Where it is strong and where it's weaker, they're further apart. So I'd like you to add this into your diagram as well. So up here, where they are far apart, we would say it's weak, and down here, where they're closer together, we would say that it is stronger. No. It's because if they were any closer, they'd hit people in the head. Like, why are they way out there? Okay. And this follows what we call the inverse square law. Okay? Other examples of things that follow the inverse square law are magnetic fields, sound, light. As you get farther and farther away from light, it gets dimmer and dimmer, and it follows this inverse square law. And more on the inverse square law coming up. Okay, so the key ideas there are where the field lines are close together is where it's strong, and where it's weaker, they're further apart. That's the key idea. This diagram implies that gravity is weaker as you climb in altitude, right? As you go higher and higher and higher, I've talked about this before, gravity becomes weaker, right? So if you were to graph gravity at different altitudes, what do you think it would look like? What would be the shape of it? As you get higher and higher,
We're talking like sea level up. Like
yeah,
vertical stuff.
altitude, as you go higher in altitude, what would the gravity do? Decrease, right? So what would it look like falling? Shape.
Go down.
Like that, maybe?
Yeah.
Yeah.
I feel like that's wrong though.
You feel like that's wrong. What's another way it could go down?
Yeah.
Does that feel more right? Yeah? Why does that feel more right?
Because once like up until like a certain point in like our atmosphere, you're still gonna have like a big gravity, and then once you're out of that.
You think it has to do with the atmosphere? It's because it's an inverse square relationship, right? So it's 1 over x squared. So it's inverse, so it's like that. It's not a direct relationship, it's an inverse squared. So it kind of looks like this. So right here, 9.8, like at 0, the value would be 9.8. Right? And at about 400 kilometers up, it would be about 9.5 newtons per kilogram. Only 9.5 newtons per kilogram. Where's mine? Oh, there it is. Megan, can I have the bathroom scale there? Mine?
Oh, yeah, sure.
So if I were to take my nerd bathroom scale and I went up 400 kilometers and jumped on it, well, instead of weighing, okay, that can't be. There we go. Instead of weighing 800 newtons, I would weigh like about 760, 770 maybe. 400 kilometers up. That's a long ways. 400 kilometers, that's like to Winnipeg up.
How can we like calculate our weight?
Tough to do.
That's why I asked. So,
How can you calculate your weight in space? You can't even do that because there's no gravity.
You can't. And that's what we're going to talk about. There is gravity, that's what I'm saying. That's exactly what I'm saying here. Notice that at an altitude of about 400 kilometers, gravity still pulls at about 9.5 newtons per kilogram. And I've got Space Shuttle, which shows you just how long ago I made these notes, because the Space Shuttle's been like decommissioned for about 15 years now. So we'll say International Space Station. Let me get to you a sec, Colin. Aren't ISS astronauts experiencing weightlessness? They're 400 kilometers up. They should weigh, guys my size, should weigh 775 newtons. But they don't. They appear to be weightless. You've seen the video. You've seen them all floating around up there, right? What's going on? Riley's got it. The space shuttle astronauts and anything else in orbit, and this is a key idea, are actually falling forever. They are indeed free falling, just like Tom Petty sang. They just never land. How can they not land? I mean, if you've fallen, there's lots of gravity. I'm telling you, it's 9.5 newtons per kilogram. It's 9.5 newtons per kilogram. It's like 95% of what it is on Earth. They're just falling. But they're not falling straight down. What are they doing? They're moving horizontally and falling. Now, when I throw the ball, Colin throws it back at me, eventually it gets to me and then we catch it, or it hits the ground, right? But what if you're going so fast that you actually go so fast that you curve around the Earth. Does that kind of make sense? Can you see it visually? It's not how you curve a bullet, no. Right? If you think about the object, whatever it is, the ISS or the satellite or whatever it is, right? Not only is it falling, so it has a vertical component, but it's also going horizontally, right? So where does it end up going? It goes there. But because you're over the corner kind of thing, right? At that point there, you're trying to do this, but you're also going this way, and so you end up going that way. And then here, you're falling like that, but you're trying to go this way, so you end up going like this. And so you just keep on going and going around the corner of the Earth, falling off the edge of the Earth, if you will. Right? You end up in orbit. You are free falling forever, but also moving sideways. You're falling and also moving sideways. You are in orbit. The vector sum of the horizontal motion and gravity causes the shuttle to orbit the Earth at high speed. Since gravity is constantly pulling down the astronauts, they are in constant free fall, which is apparent weightlessness. You seem to be weightless. They actually do have a weight, it just can't be measured. If I were to take my 1 kilogram mass, and I'm going to talk some more about weight in a while, if I were to take my 1 kilogram mass and hook it up to my thing, and watch carefully, if I were to let it go, what did it do? It went to 0. How come? Because they're both falling. Right? So Logan asked, how do you measure the weight of the astronauts on the ISS or the shuttle? You can't, because everything is falling, and so it shows 0. That's why astronauts are pure weightless. It's not because there's no gravity there. There's a lot of gravity. They're just, say it right, free falling. Everything. I should, yeah. You could sing it first. Colin has a question. Oh, yeah.
So, like,
well, you would eventually, seeing as Earth is the closest, yeah, Earth is the closest planet, right? Depends on your trajectory too, right? They actually use gravity, like when they're sending long-distance probes, like out to Pluto, they'll spiral it where it's going to intercept with Saturn, and then they use the gravitational field to sort of slingshot it, kind of in another direction, and speed it up, like they did in The Martian, exactly. It's an awesome movie. Some good science going on there. Too much bad language. Bad language in that movie. Okay, should we watch another TED Talk?
yeah.
9.8 times 1.5. 14.7, and that's going to be negative 14.7. And now I'm going to throw that into this one over here. And we know that the VI is 0, right? So really, it's just going to be...
Oh, can we use the VF?
No, not until you can show me the derivation to use it, where it came from. Yeah, well, I'm not a trusted source.
So can I Google it?
You can only use it if you can derive it. Means, like, show me where it comes from. There's your answer. Oh, start. How high is it? We're solving for the distance, right? The formula that has distance in it is the one with V bar. So V bar equals d over t, but I don't got V bar yet. So I'm going to move that over here. Yeah, I got to find that average first, right? So 0 plus negative 14.7 divided by 2, 7.35, I think, right? And then multiply by 1.5. Notice how I'm still writing my formulas out. And I'm including units. The units were pretty good on the last test. I had high hopes, I had intentions on deducting marks for no units, and then when I had entered everything into the computer, I went, oh, I forgot to do that. So my laziness benefited you. 7.35, that's the average velocity, that's meters per second. So, Jasmine? Negative, right. Right. Now, actually, I guess that means that the D, the displacement, is actually negative 11. So why is that negative? Well, because it's going down, right? The displacement is that. So in this case here, does it matter that it's negative? Because the question really says, how high is the ride? Would I accept minus 11? Sure. I guess the answer to the question, how high is it? It's really 11 meters high, but I'm pretty flexible. I can touch my toes. I can. You laugh, but you don't think I can. Oh.
So if I find out where that is.
Are you ready to try example number 2?
Neighborhoods?
Yeah, I think there's 4 pages, isn't there?
There's four. Yeah, four. I know. And there's one to the one side.
I think you kind of slipped up on this.
Yeah, I did.
That's okay.
Grade 12. A tennis ball is thrown upward with an initial velocity of plus 22.5 meters per second. It's caught at the same distance above the ground from which it is thrown. So I'm just going to draw a picture here. Here's my stick person with the big head. And they throw the ball up and they catch it at the same height. So in other words, the overall displacement is 0. You could, yeah. You know what the muzzle velocity is. It's easy. Yep. 6,000 seems a little high. But the question here is, how high does the ball rise? So my initial velocity is 22.5. Now, what would be my final velocity? 0? Where is it 0? No, it's actually minus 22.5 when you catch it. It's 0 at the peak, right? Yep.
So your average velocity.
Your average velocity would be 0. Well, the final velocity on the upwards trip is 0. So that's what we're going to worry about, right? How high does the ball rise? So how high is a D value? But to get the D value, I need the average. So the average is pretty easy to find, right? VI plus VF over 2. So it's 22.5 plus 0 over 2, which is 11.25. Oh, but we don't know the time, do we?
No.
I think I have to do part B first, looks like. I know, to get the displacement, to go V bar equals D over T, I'm going to need the time. So I got to do part B first. I got to fix this. So how am I going to get how long? A is minus 9.8, right? I don't know the change in velocity, but I can get it pretty easy. The change in velocity is the final minus the initial, which is 0 minus 22.5. So the change is minus 22.5. Do you need to show this step, do you think? It doesn't hurt, but you could probably just know, okay, you can just do that part in your head if you want. So A equals delta V over delta T. Minus 9.8 is minus 22.5 over the time. And I've said this many times, you've got to be able to solve equations like that without even thinking. Right? You need to know the process there. I get 2.3 seconds. You guys get something like that? Anybody try it?
Yeah.
2.3 seconds, and then now I'm going to put this up here, right? 25.9. So now, if I'd shown you that like about 6 weeks ago, you probably would have, your brain would have exploded. But now you're like, oh yeah, that's easy. I can do that.
I think writing it down is like confusing me.
Really?
But like once I look at it, I do it myself.
Yeah. B, the answer is how long does the ball remain in the air? Does the ball remain in the air 2.3 seconds? That's actually 2.3 up, isn't it? So really, that's right. The total time is going to be 2.3 plus 2.3 or 4.6 seconds. Excellent.
Knowledge.
Glad you still.
Cat. Now, Canada's Wonderland actually does have a drop rod that's 70.1 meters tall, and I have been there, and I actually did time to see how long it took because I wanted to know how tall it was. And I just
Do you have one of those like little tiebacks?
just a regular digital watch, yeah.
Where you like have to talk to them?
That was a long time ago. I mean, if I'd had a phone now, it would have been pretty easy, right?
Oh, that's good.
How fast are you going when you reach the bottom of the ride? If it takes you 3.8 seconds to complete the ride. So A equals delta V over delta T. So minus 9.8 is equal to delta V over the time.
How much work you have to do to better?
Wait, if we did that on the test.
You have to show me you know the formula, the derivation.
Show you that we know the formula.
I'll grant you rights. You have to do it like from scratch, blank sheet of paper. 37.24 meters per second. Now, since the VI is 0, that means that the final velocity is minus 37.24 meters per second, which is, by the way, is that right? 134 kilometers per hour? Yeah, that's fast.
Oh, that wasn't part of the question.
No, I know. But that's it. That's pretty easy, really, isn't it? All right, I'm going to give you a hint here. Suppose the ball is dropped from a tower 70 meters high. How far will it have fallen after 1 second? So, 1 second. How far does it fall in 2 seconds? And then during the 4th second. So just that 4th second. So the 4th second, 0 to 1 is the 1st second. 1 to 2 is the 2nd second. 2 to 3 is the 3rd. So 3 to 4 is the 4th. So you want to know how far does it fall between the 3rd and the 4th. So you got to figure out where is it after 3 seconds and where is it after 4 seconds. You know what? Let's not do A and B.
Oh, what the heck?
Let's not do A and B because it's all going to be the same. You tell me where it is after 3 seconds. You tell me where it is after 4 seconds. And then how far does it fall in that 4th second? No, between 3 and 4 seconds. How far does it fall? How far does it go between
From 3.
there to there? Between, that's 3 seconds, that's 4 seconds. So tell me, you have to find the distance it fell after 3 seconds and the distance it fell after 4 seconds, and then subtract.
Wait, we're not doing 1 and 2?
No.
No.
Should I do this one?
No. Yes.
No.
Okay, I'm gonna do it. Where is it after 3 seconds? I know my acceleration is minus 9.8. I know my time is 3. I want to know how far. D equals, I'm solving for displacement.
Isn't these?
I need to find average velocity, don't I, right?
Yeah.
Okay, so I got to find out how fast it's going at 3 seconds. So,
D isn't 70?
no, different question, Riley.
Yeah.
So how fast is it going after 3 seconds? I think we know this already, don't we? .4, which makes my average velocity 14.7, technically negative. So it has fallen 44.1 after 3 seconds, right? It's at a spot of 44.1 after 3 seconds. How do I do it for 4 seconds? Just repeat, right? Just repeat. Rinse and repeat. .78 is where it is after 4 seconds. No, how far did it fall during that time?
Oh, so 78.
This would be like 7 marks, wouldn't it? Right, you're going to subtract them. 34.3. It falls 34.3 meters in just that 1 second, which is almost as far as it fell after 3. How come it fell so much farther? It's going faster, right? Think about those dots. Remember the fat cat? Right? The dots are going to be getting further and further apart. It hasn't reached terminal velocity yet, no. Okay, time for me to be quiet. I gave you a sheet. I generally don't give this sheet out second, but I've discovered over the years that this sheet is actually easier than the first one that I give out. So I've rejigged things. It's called extra problems on the solutions, but it shouldn't cause too much for you. I reset it to gravity problem set number 1. There is a QR code. There is a link for you. There's a couple questions, number 6 and 7, that are weight ones that I have to still talk about. So you can just leave those out. I'll pull those out eventually. You should do. There's only 7 to do on there, and some of them are pretty easy. Although having said that, I know number 3 is a little bit challenging. So do as many as you can tonight. I'm going to put these in the "What Did I Miss" binder. I should date them too, eh? Okay, that's good.